All right, welcome back for part 2 of the notes. And so now we're on the back of that front page. We're going to fill out these 5. We've got 5 problems. So for number 6, let's go to the top here. If you double the radius of a sphere, what happens to its area and what happens to its volume? Now the thing about this, if you take a sphere, if you double it, first of all, we're talking about similar solids, similar figures that are three-dimensional. So this is a DAV problem. This only works, a squared, b squared, a cubed, b cubed. It only works if you have similar figures. And in this case, we do. So if you double the radius of a sphere, that's actually a 2-to-1 ratio. The first sphere is going to be 2 times the size of the second sphere. That's a 2-to-1 ratio. So for the area, what would happen is we would square both of those numbers, and what that gives us is 4-to-1. So the area is 4 times greater. 4 times greater. If you double the radius of the sphere, the area actually increases 4 times. Not 2 times. It doesn't double the area, it quadruples it. And for the volume, the space inside, we would raise each of these numbers to the third. 2 to the third is 8. 1 to the third is 1. So if this was a balloon, and let's say you doubled the radius of the balloon, what is that going to do to the amount of space inside, the air inside? It's actually going to be, the volume is 8 times greater. 8 times greater. Okay, so what happens is your numbers, especially when you're cubing, they can get very big very fast. Okay, if you're not sure about this, you could draw a sphere, and you could pick a value. Let's say the small one, the radius is 3. And if I double that, then the new radius would be 6, and the ratio of distance is 6 to 3, okay, or 6 over 3, but that reduces to 2 over 1. Okay, so there's my 2-to-1 ratio right there. All right, so number 7, if you triple the length of each side of a square, what happens to its area? All right, here's a big one, here's a small one. Let's say the small one, the dimensions are 1. If I triple that, the dimensions are now 3. So what happens, the ratio of distance is 3-to-1. It's a 3-to-1 ratio. What happens to the area? Well, to go from the distance ratio to the area ratio, we are going to square both numbers. 3 squared is 3 times 3, which is 9. 1 squared is 1. So what happens to the area? It will be 9 times greater. 9 times greater. Now it's not volume because these are 2-dimensional. It's not a cube, it's a square. So we're going to ignore the volume. And so number 7 is done. Number 8. The ratio of the surface areas of 2 cones is 25 to 49. Find the ratio of their volumes. The ratio of the surface areas. Let's add the word similar in there. We really need to know that they would be similar cones. Ratio of surface area is 25 to 49. The key word here is area. You see, when I get my number 25 to 49, my ratio, I have to figure out where to put it. Is it D, A, or V? Now in this case, it's the ratio of surface areas. So I'm going to put 25 to 49 in the A ratio. That is surface area, also lateral area, 25 to 49. The question is, find the ratio of their volumes. So what we need is the volume ratio, but to get that, you have to first go back to distance. So to go from, this is a squared, b squared, to go back to ab, you have to square root. So square root of 25 is 5. Square root of 49 is 7. So the distance ratio is 5 to 7. How do I go from distance to volume? I raise each of those numbers to the third power. Okay, I'll do it on the calculator this time. So 5 to the third is 125. And 7 raised to the third power is 343. So we've got 125 to 343. That's the answer. Okay, you've got to be careful as you're doing this. You have to make sure that you're answering what they're asking. They wanted the volume. This is the volume. You know, so don't stop when you get 5 to 7. You got to find the volume ratio. And that's it. That problem is done. Number 9, the lateral areas of two similar cones are 8 pi and 50 pi. What is the ratio of their volumes? So these numbers are for the areas, but what we really want is volume. Because we're dealing with similar figures, I'm going to set up a DAV. Now, 8 pi and 50 pi are for the areas, but here's the thing. I'm not going to put 8 pi to 50 pi in my ratio. I'm going to write it as a fraction first so I can reduce it. Because look what happens here. Pi divided by pi is 1. 8 divided by 50, you can divide each of those by 2, and what we get is 4 over 25. Now that's reduced. That is my ratio for area. And that should look nice to you because when you see those two numbers, that's a perfect square and that's a perfect square. So what do we want? What's the question? What is the ratio of their volumes? Well, to get the volume ratio, you first have to get the distance ratio. So we're going to go back. We're going to take the square root of both of those. The square root of 24 is 2, and the square root of 25 is 5. So that would be the ratio of distances. Maybe that would be the radius. Maybe that would be the heights. What we want, though, is the volume ratio. So how do we get from distance ratio to volume ratio? We're going to raise those numbers to the third power. So you're going to do 2 cubed and 5 cubed. So we're going to get 8, and 5 cubed is 125. So the ratio of volume is 8 to 125. Okay, so that's number 9. All right, now number 10. Let's go ahead and read it first. The ratio of volumes for two similar solids is 125 to 64. The ratio of volumes is 125 to 64. Okay, they give us that. That's nice. If the surface area of the larger solid is 50 square centimeters, what is the surface area of the smaller solid? If the surface area of the larger solid is 50 square centimeters, what's the surface area of the smaller solid? Well, they're asking about surface areas, but they give you information about volume. Similar solids, so that tells me it's a clue. This is a DAV problem, distance area volume. They give us the ratio of volumes, 125 to 64. Now they're asking about surface area, so we've got to come up with the area ratio. So first of all, to get from volume back to distance, we have to take the cube root of both numbers. So the cube root of 125 is 5, the cube root of 64 is 4. Now that's the distance ratio. We're talking about surface area. We need the area ratio. How do we go from distance to area? We square both numbers. 5 squared is 25. 4 squared is 16. All right, now here's the thing. At this point, we're not done because they don't ask for the ratio of area. They're actually asking for one of the actual surface areas of the smaller solid. If the surface area of the larger solid is 50, what's the surface area of the smaller one? So what we're going to do here is actually make a proportion. So we're going to set up two fractions. Now, the larger solid is 50 centimeters squared. What is the surface area of the smaller one? I'm going to call that x. So what's my other ratio, though? I mean, I've got three sets of ratios, 5 to 4, 25 to 16, 125 to 64. Which one do I use? Well, they actually tell me in the question. They're talking about surface area. So I've got to use the area ratio. If these were heights, then I would be using distance ratio. If these were volumes, I would be using volume ratio. But in this case, I'm using area. 50 is for larger, X is for smaller. So the larger number in the ratio is 25, so that also goes on top. The smaller number is 16, so it also goes on the bottom. How do we solve a proportion? We cross multiply, so that's 25 times X equals 50 times 16 is 800, and now we divide by 25, and the answer is going to be 32. Now this is the surface area, square centimeters, so centimeters squared. That is your solution. So what you had to do was get the ratio so that you could then create the proportion. And that is the end of part 2.